Okay, so we were discussing the supervised or inductive learning, and the main points what we have said in the earlier classes, and that in the supervised setting, a set of just a second, yeah, a set of examples is being given, and we try to find out a function from this example, or we devise a function that's called target function from this example, so that that can accurately or precisely say the this class relationship or kind of class belongingness, the new images or new examples. Okay, so it is a pure induction task. The given a collection of example of f, return a function h that approximate f. So this is basically f is a kind of hypothetical function, and we are trying to find when a hypothesis function that h, and that is going to estimate the f. So find a hypothesis h such that h is going to estimate or closely estimate f given a training set of examples. So this is basically the idea of supervised learning concept. So why supervised? That is the given training examples. So that is examples. So that is most important things. Training examples are given. So this is a highly simplified model of real learning that it ignores prior knowledge. So there is not prior we have used here, and these examples are being given. That is important. So now the question is that how you are going to find out this hypothesis over let's say this is going to a your some data is given. Okay, so now these are the data, and now you how are you going to get a, but if it is a that what we have seen so far, we can get a line, or we can get a kind of curve, something like that. So that kind of thing we can predict. Okay, or we can hypothesize. So construct address h to agree with f on the training set. So what we're trying to say that we are trying to find out h. This is the hypothesis function, so that it's closely related to f. F is the kind of idealistic setting that f is basically the function given of these data points. And with f on all examples, so it is a kind of a curve fitting example. So this may be a linear curve that you can see. Okay, or it may be a some sort of this curve is non-linear curve, or a, some polynomial um, of some lower degree, and maybe and some polynomial with higher degree or something in this way. Okay, so the way it is been curve fitting kind of example, or we can say this kind of curve also is possible. Now the thing is that one is the major important thing. We have shown that so many curves in for these example patterns or examples point. Now this may be linear. It's a very this linear is means what? It is a very simple in nature. So this is simple. Simple means it is the model complexity is very less. So simple in that sense, the model complexity is less, is very less. Now we can say, so that is a kind of linear complexity. Now the thing is that we can go for a bit complex. Okay, so bit complex is a curve, or a curve of smaller degree of polynomial. Let's say it's a basically, you can say it's a kind of circle. It can be kind of this kind of things, parabola kind of thing. So now it's possible that we can go for a some higher degree of polynomial. So it's a more complex. So the higher degree of polynomial. So now the question is that which particular curve is going to be most suitable or optimal, you can say. So we go and go for more complex to more accurately this curve, and if we go extremely complex kind of this will just a very complex thing and may not be that much desirable. So this is a kind of open question that I just want to ask you all, that what will be our design criteria? If it is a simplistic, or it will be a very complex, or what will be what is actually, this is very important question, and we have to basically addressing this issue very in a very detailed manner. Okay? So what is the complexity of the car or model? So this is one thing that in this particular concept is very interesting. That's called Oakman's razor. But this is we always say prefer a simplest hypothesis. We the curve simplest hypothesis, but it is consistent of data. Consist of the data means basically the examples. Okay. So this is important, that we need a kind of curve that is simple enough, but it will accurately represent the data, given data. So that is one of the important things. Okay. So under this supervised setting, we mainly, there's two things we have to very important. If one we said that if it is a x-axis, this is y-axis. Now this y-axis is basically the class belongingness. If it is a kind of you can say continuous, this y is continuous, then it is called regression. Okay, so this continuous function, so y is a continuous, and if y is a basically discrete, this y and this it is in general called classification. Okay, so learning discrete function is called classification. So it's a kind of Boolean function. This may be a binary classifier or multi-class classifier, binary multi-class.
Excuse me, sir.
Yes.
Sir, in the previous slide, what do you mean data is consistent? I mean, if I use more degree of accuracy, the data will be more consistent. Where do I stop exactly?
That actually I said that I said that is a good question. That definitely that, but still now if I said that is okay. What I'm trying to say, this is a good question. So what we said that these are the data, and we go for a now you can say that you go for a this kind of curve. That is consistent of data. Now you say that this is consistent. Question is that if this data is something like that, now this is a very a kind of a easy situation. Okay, easy means very idealistic situation, but sometimes it may happen that some data is here. Okay, now this data may be or may not be a very actual example. So now the thing is that what we have said in supervised setting, these examples are given. Okay, these examples are given. But if we say these examples are is perfect, now it may not always the case. So maybe there is a some sort of data which may be kind of noisy in nature. So some kind of accumulation noise. You are basically these data sensor based data. Now when you just for example snapping some image. So what happened? There may be using so your hand is somewhat shaking or something. That may be some acquisition noise, or there is some sort of sensor noise, or some compression noise, some environmental noise can come. Even when you are sampling, you are just for you can say nowadays is a very pandemic situation. The data we have to make a statistical model to find out that what is the nature of the this pandemic in next year or next to next year. So that data is not always be a very perfect data. Okay, that is one of the major problem. In practical situation is important, but in a lab setup you can say that all the data is perfect and you can go for that. But it's not always the case. Some data is noisy. Maybe I'm not saying I don't know this noisy or not noisy. Maybe this is the actual data. Maybe here is a sharp A. That may be possible also, but that you don't know. So at this situation, what will be even if you consider this situation, what will be your optimal curve to that? So in general, this I will definitely come in this particular because this is one of the important concept, most concept that called the generalization criteria of your model. So the basic thing is that what generally we do in this particular case, we we are trying to find out a curve, or it may be linear or maybe non-linear, but idea is we go for a curve that is consistent with data but without losing the generality of the data distribution. So this is now the it is bit tough. Who don't have the concept machine learning prior concept prior idea. So what exactly it is, but something like that. We are as a whole, we are trying to represent a data set with our hypothesis function, it whatever function is maybe, but that we at the same time without loss of generality. That means we generally think that most of the data points is consisting with a particular data distribution, and with this data distribution we will go. Maybe some point it's outlier, or maybe some odd thing that maybe happen, but maybe we are not going to consider this maybe thing, or this outlier, or kind of a very odd. So this is the answer, and how we're going to achieve this is the concept, and how we're going to achieve it we'll see in the it's not we will see in the next lectures. Okay, got your point?
Yes, sir. Thank you.
Okay. So here the thing is that we are trying to find out the regression and classification. These are two basic of examples of method supervised method. So as you said that regression is a continuous output and classification is discrete output. And we start with the regression. Okay. So at already we that particular example given, and better to start with the old example. So here you can see here that this is the housing price example. This is the square feet of the size of the house, and square feet, and this is a dollar. It's a the $1,000 scale. So the thing is that these cut marks or these points are being given as examples. So these are the training samples. Okay. So so now what is the important? that given these training samples, can we find out a curve? That curve is very consistent with these samples. Okay, so very hypothetically, we try to find out a curve. It is a linear for our understanding. It is a linear or non-linear is not a big issue, but is that we are for understanding that we can, okay, this is let this is our curve. Okay, so given the right answer for each example of the, so what is the purpose of this curve? Now, the purpose is that in a point where this curve marks is, now let's say this in between these 2 points. So if this point we know, so okay, this is our the square feet. It is just slightly less than the 1,000 square feet. What will be its cost? So definitely its cost is something like this. So this is the cost, and this is the so this is the basic idea. Okay, so now the major purpose of this line is that, so any, if you get this line for any for x value, we can get the y value, and you see the y value is continuous in nature, and that's why it is called regression. Now the thing, another important thing is important. Why it is called linear regression? Because our hypothesis, this is our hypothesis function. This hypothesis function is linear in nature. So for, since it is a two-dimensional data space, it's a 2D feature space, two-dimensional feature space. So our, this line is basically a linear, a line. So regression is called going to predict the real value data. So here, what is this? That basically it is the how notation is being given. So size in the feet square. So this is the examples, or better to say training example. So this is the 2104 square feet, and it is a this into $1,000. So this is the way. So this is x and y pair. So x is your x value. This is the square feet, and y is the 46 into $1,000 kind of thing. Now, what is M? So number of training samples. So how many such kind of samples, if the cardinality of this set is basically M, the total number of M samples given. X is the input variable, that is this X, and Y is the output variable, this is the target or basically label. So XY is one training sample, and is basically ith training samples is basically given the X of I, Y of I, something like that. So these are the just notation. Okay, now. So that part we know, that part is just given. The training set, what are you given here? This is the training set. Okay. Now, based on this training set, we are going to find a training learning algorithm. So that is important, that we are going to find out that how we are going to get learning algorithm. Then, if we get this learning algorithm, we can, using this learning algorithm, we get age. And when we get age, then if you get any house size of the house, we can get this. So the first concept what we have to learn, what is age. So since it's a linear regression, so and we are used the 2D data space, this age is basically a line. So what is line? Okay. So line is, this equation is this. So this is a kind of two parameters. One is slope, one is constant. So this age is a parametric function of these two parameters, h, a, and c. You can see that here you see that this represented h theta x is basically, we can say for hx is theta 0, that is a constant, and this is mx m, this is m, that is this is slope, and this is the x. So this is exactly what I said, that y is equal to mx plus c in this format. And you see, since this theta 0, theta 1, this were m and c basically, these are two parameters. So this is a parametric model, and this parametric model, these two are theta 0, theta 1 parameter. Okay. Now you can see that this particular thing, that these data samples are given, this hx is a, what is only one variable. So one variable x, and this girl univariate. So this is univariate linear regression. Since we use this for our hypothesis is a very simple, and this is only one function. This is x, function x. Okay, so linear regression with one variable, and since one variable is called univariate. So now this is the your training set that you said. These are the training set, as we explained earlier. This is the training set, as we know. This x, this is corresponding, this is x, and this is corresponding y, and this is basically a x I y I pair, and maybe I is equal to 1 to m. So these have been given. Now using these values, or this pair value, we have to try to find out the hypothesis of that. So h theta x is theta 0 plus theta 1 x. So that means what I said, this is a line equation. So, so now thetas are theta 1s, theta 0 are parameters. This theta, it is theta I over theta 1's parameter. The question is how to choose this theta 1. So the question is theta I, we have to find out. Here theta I is basically theta 0 and theta 1. And then how to choose these two, theta 0, theta 1. Now that is now the problem boiled down here. Okay. Now you see. So better, this is called hypothesis function, and it's a linear. In this case, our thing is linear. Okay. So linear discipline. Now, what do you mean by if theta is equal to 0, theta 0 is equal to 1.5 and theta 1 is equal to, now what theta 1? Theta 1, for your understanding, I'm saying theta 1 is basically the slope. Okay. And theta 0 is the constant term. That means C. So y is equal to mx. That is for your understanding. Right. So this m, now you see here, since it is a theta 1 is equal to m slope. Now slope is what? The slope is 0. So it is a kind of a straight line. Yeah. And what is this? This is 1.5. Because theta 1, theta 0 is equal to 1.5. Okay. And now you can say that if we can say that, okay, now we can put theta 1, that means m is equal to 0.5. Okay, so 0.5 means what? And then y is equal to 0.5x and is equal to 0. That means so that, and theta is equal to 0. Theta 0 is equal to 0. So then definitely there is some uh, line is basically the slope is there, and slope is something like that. And why it is coming to the center? Because this particular line is theta 1, sorry, theta 0 is equal to 0. So it is passes to the origin. Okay. Now if we see that we put y is equal to 0.5x plus something like, let's say 1. Okay. So theta 0 is 1 and theta 1 is equal to 0.5. Now you just think the same line is basically shifted here from here to here. This is 1. So because it is a theta 0. and this slope, this curvature is there, this inclination is there, that means it's theta 0.5. So in this way, what we can understand from this, that changing or varying theta 0 and theta 1, we can get different hypothesis function. And what is our target? We now we understand how to get, how to changing the different theta 0, theta 1. So different parameter, how to get these lines. But what is our thing? Our thing is we get a line so that our these example points are very well represented. Okay, so that is the point. That is we're going to write, trying to understand. So how we are going to understand this? This is called that we theta 0 choose theta 0 theta 1 such a way that h theta x is close to y. Y means what? That is the imaginary line for our training example y. Okay, so let's say that we are trying to find out a such line with theta 0 and theta 1. Such line is this theta 0 theta 1 is basically the parametric equation of straight line. So the parameters of this straight line, and such that so we can better accurately represent these data points. But how we can do that? So let we understand this is our hypothesis, this is our parameter that we understand. Now what we're going to do, now you see that this h theta basically is your hypothesis function. Let's say it's univariate, and now it is going to give you a file of x of I. Okay, so this is going to you predict. So actually what does this mean? That means actually this. So if this particular thing, if you say that this point, so actually this point is predicted by this, and this, but this is the actual point. Okay, so this point is given by this term, this h theta x of I. Okay, minus or the corresponding actual value of y of I. So this is the actual y of I, and this is the predict of this was h theta of xi. These two, and we're taking the difference. And when we're taking the difference, we take the square difference. Okay. Now this square difference, we going to sum up for all the data points here, whatever the data points. So let data points is what? Number of data points is m, so it is 1. Then we do a kind of normalization. This is a normalization factor, and this is going to be the, you can say, the loss function. This is the loss for this particular line. And what is our actual job? To this is square error function or loss function, and you can say here it is called cost function. More technical term is a cost function. And what is our job? To minimize this cost function. So what do you mean by the minimize? If you are going to minimize this cost function, then the line is going to be very, very close to these points. Okay, so the idea is that this is a kind of optimization function, optimization procedure, optimization function. So that we have some objective function, this, that j theta 0 theta 1 is your objective function or cost function, and that we are going to minimize to optimize this. Minimization is a kind of optimization function. And here m is the number of training samples. Still, who is not understood? So that is our goal. Now you see that we understand that here is that we can understand the h theta of x we can get from the training samples. That we have done. Fine. Now the thing is that for so this h theta for each h of theta x. So what is this? This for h of theta x, this is a line, and for that line there is a some sort of error. Okay. So if I plot this h theta 0 theta 1, okay, this is the theta 0 and theta 1, and for a different theta 0 theta 1 for then this is basically a error surface. Okay, now error surface is what? For a different theta 0 theta 1. So the one set of theta 0 theta 1 means one line, and every this line giving a cost. So now this you see this theta 0 theta 1 is a up 2D kind of curvature. Okay. So this is your theta 0 theta. So if we plot this theta 0 theta 1, it is a 2D this kind of curvature. And what is your, let's say this is theta 0 theta 1. This is the, this line is basically given a particular theta 0 theta 1. Now what do you mean by the minimizing your cost function? That means we have to find out this end point here. So the lowest points of this error surface. Now here there is a big question is that what is the nature of this error surface? Now you see, you can see that this error surface is convex in nature. If this convexity is assured, okay, if the convexity is assured for a particular search space, then this kind of algorithm will going to give you a local or global media. Because if the convexity is assured, then the local global media is more or less same. Okay. So that is one of the major aspect that we have to take care. So the particular problem we are taking, then this error surface is convex in nature, then we can assure to get the global optima as a local optima. Now, what is basically we another important nomenclature is called contour plots. The same thing. Basically, you see that this particular scene or this particular now, if I bisect this in this way, in this way you are bisecting. Okay, just bisecting it. Now, bisecting it means what? If you were just take a oval shaped thing and take a bisection, bisection of this, it essentially give you some sort of the end of concyclic ellipses because you're taking the subsection out. Just kind of this kind of thing will come up. Roughly, I've said the exactly same thing has happened here. So here you can see that these plots are taking the bisection of this particular error surface, bisection of this. You bisect it. And you can say these are the concyclic ellipses. So this is a concentric. So these ellipses will come, and these ellipses will called the contour or contour plots. Since this is a plotting. So one is very important to understand that in a particular contour, that means what? It is a particular same distance, because these contours are basically same distance from here. So this is a particular contour, means in a particular in a error surface you can see, if you in a rough surface, if you are here, a kind of here, and similar thing if you are it is if you are a concentric circular kind of thing, this you are pointing here or something like that here. So the thing is that in a contour in a particular point, that if you are in a particular theta 0 and theta 1, you are in a particular contour, and particular theta 0 theta 1 means what? Particular theta 0 theta 1 means line. So if a particular line here, you can see here, that means it essentially gives these points are somewhere here. Let's say you are here. Now I'm going to change it. Now what? It, you see, this line is not, because these are the points. I don't know if you can see or not. These are the points. And this line is not consistent with the points. So the distance between, we try to go, we try to find here, because this is the minimum of the error. So we are here. So distance is large, okay, relatively large. But if we go in a slightly better curve, something like that, you see, where are we? We are a bit closer center. Go again. We go different in larger, that in a distance from. Now you see we are almost center. Now this particular line is very consistent and relatively for other lines to these data points, so that we are very close to this center of the error surface. So one thing is very important here, that we are trying to find out what, trying to find what is our goal. To find is easy if the surface is convex. Convex in nature. Okay. And the corresponding the lines, that is something like that. Okay, so the thing, so the algorithm will follow, the corresponding algorithm to find the surface minima, or local, or you can say the we called this algorithm called the gradient descent, or in short the GD algorithm. So what is the we going to do? We use some function j theta 0 theta 1, we have to find the minimum of the surface. We start with the arbitrary theta 0, theta 1. Arbitrary theta 0 will start, and we keep changing theta 0 time so that we can reduce this j theta 0, theta 1. That is the idea. So until we hopefully end up a minimum. So if I say diagrammatically how it look like. Now you see I am taking some practical scenario. A surface is not convex in nature. So if this is the case, what we are going to do, you see, here we are starting point. So any theta 0, theta 1, any arbitrarily theta 0, theta 1. And then we keep changing theta 0, theta 1. So that what we can get? So we are here. So we start with here. So we change, we are 0, theta 0, theta 1 here. Now we change, let's say theta 0 plus alpha plus theta 0, theta 1 plus beta. So that we change. And we get back here. And then again you can say theta 0 plus 2 alpha, theta 1 plus 2 beta, something like that. Arbitrarily we are changing. They're coming here and so on. There is no guided search. At this moment, we are basically doing some random changes. Okay. And again, another interesting, if we change this initial point, something different. If we change this initial point here, rather than this, if we start from here, then we can, rather than go to this local minima, we can go to this local minima. So here, the problem is the multiple local minima. So now if we say, if we end up with this local minima, and this local minima is lower than or minimum more, it is basically smaller than this, we are trapped in this local minimum. We never get out from here with this algorithm. So that is one of the disadvantage of this graduation algorithm, a normal graduation.
So here by local minima you mean the one which is closest to zero.
Zero means
Like local minima means the one which is closest to zero, or like j of theta not theta 1 can go even lower than zero.
no. The thing is that what I'm trying to say, that if you say that this is a convex thing, and this is not, I'm line just saying one univariate. That means if you are here, and this is the local minima, and here it is a local
So
minimum. Yes, please.
we want j to be as close as to zero.
No. How no? How can you know that it is going to zero? It never be zero. There should be, you
No,
never
I'm just
see.
asking. We want j to be as close as it would be to zero.
Not necessarily. You never be come up with, yeah. Idealistically, that if you find that there is no error at all, if you are a kind of a curve that is just touching every point, that is zero definitely. But it may not, practically it is not the case. It depends on so many things. In general, with linear hypothesis function, you cannot get the zero as a your minima. So it depends on that how you choose your hypothesis function. Your error function will depends on this.
So j could be positive or negative both.
Positive or negative, I cannot. No, you are taking a square root. How can it negative?
Oh, okay. I got it.
Okay. So this is the moral of this thing. So we'll continue this lecture. So we are almost time is close. So thank you very much.
Hello.
Hello. Yes.
Sir, our aim is that given a linear hypothesis h of theta,
Hmm.
then we have to minimize j of theta, right? So, we want the cost function to be as minimum as possible. The error should be as minimum as possible. So, sir, what is the significance of m in the definition of cost function?
M.
M, the number of test samples. J is 1 by 2m times summation h of theta minus y ka whole square, right?
Hmm.
So our aim is to minimize j of theta, right?
Yes.
So, sir, what impact will m play in minimizing? Like it's a constant now, so it will not play any role.
Oh, that normalization you were saying
Yes, sir.
one by
Can you?
2m. It's just a normalization function because there is a two m number of points. When you are basically here, you can see here you are saying, na? So m is number of sharing samples. How many
Yes, sir.
times we are adding
M times.
m? So that's why is 2m is basically 1 by m. People can ask why 2, but this is just an bare normalization, nothing. It will not change anything. But total is the kind of average. M number of points we are adding, so by m. Okay. Any other question? Okay, thank you.
Why did you want to minimize half of that the average? Average is one over m times the summation, right?
That's what I said. This is just a minimization. If you 1 by m also, it's not a big issue. This is
Okay,
just
fine.
standard minimization, normalization.
Maybe that we use later. Okay, I got it. Fine. Thank you.
Yeah, yeah.